Part 1. Introduction to Alternative Cosmologies. Good evening, dear listener. As you settle into your comfortable space, allow your mind to drift gently into a state of relaxation. Imagine yourself floating effortlessly through a vast, serene cosmos, where galaxies twinkle softly against the velvet expanse of space. In this tranquil journey, we will explore alternative cosmological theories that challenge the conventional Big Bang model, a theory suggesting that our universe began from a singular explosive event approximately 13.8 billion years ago. The term cosmology refers to the study of the origin, evolution, and eventual fate of the universe. While the Big Bang theory has been the prevailing model for decades, several alternative theories offer different perspectives on the universe's beginnings and its large-scale structure. As we embark on this exploration, let your imagination wander through these diverse realms of thought, each offering a unique perspective on existence. Part 2. The Big Bounce Theory. As we continue our tranquil journey through alternative cosmologies, let's explore the Big Bounce theory, a concept suggesting that our universe's current expansion was preceded by a contraction phase, leading to a cyclical pattern of cosmic rebirths. Understanding the Big Bounce hypothesis proposes that the universe undergoes infinite cycles of expansion and contraction. Instead of originating from a singular Big Bang, the cosmos experiences a bounce at the end of each contraction phase, initiating a new expansion. This cyclical model challenges the notion of a singular beginning, offering a perspective of an eternal, self-renewing universe. So what are mechanisms behind the bounce? In this model, a contracting universe reaches a point of maximum density and temperature, where quantum gravitational effects become significant. These effects prevent the formation of a singularity, instead causing a bounce that leads to a new expansion phase. This process suggests a universe without a definitive beginning or end, but rather an infinite series of cycles. So notations of the Big Bounce theory offers intriguing implications. Though eternal cycles, the universe may be eternal, with no definitive beginning or end. So eternal, the theory addresses the problem of singularities by proposing a bounce mechanism facilitated by quantum gravitational effects. So tangle, it provides a different explanation for the observed homogeneity and flatness of the universe, challenging the necessity of cosmic inflation. So eternal's cyclical model envisioned the universe as a breathing entity, eternally contracting and expanding, each cycle giving rise to new cosmic epochs. Allow this contemplation to deepen your sense of wonder about the cosmos's infinite possibilities. Part 3. The Steady-State Theory. As we continue our serene journey through alternative cosmologies, let's explore the steady-state theory, a concept proposing that the universe has no beginning or end in time, maintaining a constant average density as it expands. Understanding the steady-state theory proposed in 1948 by Fred Hoyle, Thomas Gold, and Hermann Bondi, the steady-state theory suggests that as the universe expands, new matter is continuously created to maintain a constant density. This idea aligns with the perfect cosmological principle, which asserts that the universe is homogeneous and isotropic in both space and time, appearing the same at all times and places. The key features of the steady-state theory: continuous creation. To counteract the dilution effect of cosmic expansion, the theory posits the continuous creation of matter, primarily hydrogen atoms, throughout space. So be eternal universe. The universe is considered eternal, with no origin or end, differing from the Big Bang model's finite timeline. So be challenges to the steady-state theory. The discovery of the cosmic microwave background radiation, CMB, in 1965 provided strong evidence for the Big Bang model, as the CMB is interpreted as the afterglow of the initial explosion. The steady-state theory struggled to account for this observation, leading to a decline in its acceptance among cosmologists. So as you reflect on this theory, imagine a timeless universe where galaxies drift through an endless expanse, with new stars and worlds continually coming into existence, maintaining a cosmic equilibrium. Part 4. Plasma Cosmology. As we continue our serene journey through alternative cosmologies, let's explore plasma cosmology, a concept proposing that the dynamics of ionized gases, or plasmas, play a significant role in the large-scale structure and behavior of the universe. Understanding plasma cosmology. Plasma cosmology suggests that electromagnetic forces, in addition to gravity, are crucial in shaping cosmic structures. This theory posits that interactions between vast cosmic plasmas and magnetic fields influence the formation and behavior of galaxies, clusters, and larger structures in the universe. They were key features of plasma cosmology. Electromagnetic forces emphasizes the importance of electromagnetic interactions in cosmic evolution, considering them alongside gravitational forces. So with filamentary structures, attributes the filamentary nature of cosmic structures to the behavior of plasmas under electromagnetic forces, leading to the formation of vast cosmic filaments and sheets. Table challenges to plasma cosmology. While plasma cosmology offers intriguing perspectives, it faces challenges, lack of predictive power. Critics argue that plasma cosmology lacks the predictive power of the Big Bang model, particularly concerning the cosmic microwave background radiation, CMB. Observational evidence. The Big Bang model's predictions, such as the abundance of light elements and the CMB's characteristics, have been confirmed by observations, whereas plasma cosmology has struggled to provide equivalent predictive success. You contemplate this theory, envision the universe as a vast, interconnected web of plasma and magnetic fields, where electromagnetic interactions weave the intricate tapestry of cosmic structures. Part 5. Quasi-steady-state cosmology. As we continue our serene journey through alternative cosmologies, let's explore the quasi-steady-state cosmology, a concept proposing that the universe undergoes periodic episodes of matter creation, leading to a cyclic model of cosmic evolution. Understanding quasi-steady-state cosmology, introduced in 1993 by Fred Hoyle, Jeffrey Burbidge, and Jayant V. Narlikar, the quasi-steady-state cosmology QSSC builds upon the original steady-state theory by incorporating cyclical periods of expansion and contraction. This model suggests that the universe experiences episodic creation events, sometimes referred to as mini-bangs or little bangs, which occur within an eternal framework. These were key features of quasi-steady-state cosmology. Cyclic evolution. The universe undergoes infinite cycles of expansion and contraction, with matter creation occurring during each cycle. These were continuous matter creation, similar to the original steady-state theory. QSSC posits continuous creation of matter, but localized in space and time during these mini-bangs. These with no singular beginning. The universe is considered eternal, with no singular origin event like the Big Bang. These were challenges to quasi-steady-state cosmology, while QSSC offers an intriguing alternative to the Big Bang model. It faces several challenges. These were cosmic microwave background radiation. The uniformity and characteristics of the cosmic microwave background radiation are well explained by the Big Bang model, but pose challenges for QSSC. These were challenges of observational evidence. The distribution and properties of distant galaxies and quasars align more closely with predictions from the Big Bang model. These were challenges for state compound. The cyclic model. Imagine the universe as a timeless entity, experiencing endless cycles of creation and renewal, with galaxies and stars continually forming and dissolving in a cosmic dance. Part 6. Conformal cyclic cosmology. As we continue our tranquil journey through alternative cosmologies, let's explore conformal cyclic cosmology, CCC, a theory proposed by physicist Roger Penrose, suggesting that the universe undergoes infinite cycles, or aeons, each beginning with a Big Bang and ending in an all-encompassing expansion. Understanding conformal cyclic cosmology. Conformal cyclic cosmology posits that the universe's infinite expansion leads to a state where the distinction between time and space becomes meaningless. In this conformal state, the universe can be reimagined as the seed for a new Big Bang, initiating the next aeon. This cyclical process implies an eternal succession of universes, each emerging from the infinite expansion of its predecessor. See key features of conformal cyclic cosmology. Infinite cycles. The universe undergoes endless cycles of birth and rebirth, with each aeon transitioning smoothly into the next. See conformal transformation. The theory utilizes conformal geometry to describe the universe's transition from one aeon to another, effectively resetting the cosmos. See observable imprints. Penrose suggests that events from previous aeons could leave detectable imprints on the cosmic microwave background radiation, CMB, of our current universe. See challenges to conformal cyclic cosmology. While CCC offers an intriguing perspective, it faces challenges. See empirical evidence. Detecting imprints from previous aeons in the CMB is challenging, and current observations have not conclusively supported these predictions. See theoretical acceptance. The concept of conformal transformations at cosmic scales is complex and not universally accepted within the scientific community. See contemplate this cyclical model. Envision the universe as a phoenix, eternally rising from its own ashes, with each aeon giving birth to the next in an unending cosmic dance. Part 7. The Ekpyrotic Universe. As we continue our tranquil journey through alternative cosmologies, let's explore the Ekpyrotic universe, a concept proposing that our universe originated from the collision of higher dimensional membranes, or branes, within a higher dimensional space. Understanding the Ekpyrotic universe. The Ekpyrotic universe model suggests that our universe is a three-dimensional brane embedded within a higher dimensional space. According to this theory, the Big Bang was not the beginning of everything, but rather the result of a collision between our brane and another parallel brane. This collision released immense energy, leading to the hot, dense state we associate with the Big Bang. So your key features of the Ekpyrotic universe brane. Collision. The universe's origin is attributed to the collision of higher dimensional branes, avoiding the concept of a singularity. So your key dimensions. The model is rooted in string theory and M theory, which propose the existence of additional spatial dimensions beyond the familiar three. So your key dimension. Some versions of the Ekpyrotic model suggest a cyclic universe, with brane collisions occurring periodically, leading to repeated cycles of creation. So your key dimensions to the Ekpyrotic universe. While the Ekpyrotic model offers an intriguing alternative to the traditional Big Bang theory, it faces challenges. So your key dimension. Evidence. The predictions of the Ekpyrotic model, such as specific patterns in the cosmic microwave background radiation, have yet to be conclusively observed. So your key dimension. Evolven bistete your key dimensions, to your key dimension remains a topic of debate within the scientific community. So your key dimensiones. This design into your universe as a vast, multi-dimensional tapestry, with our three-dimensional reality being just one layer among many, periodically interacting with others in a cosmic dance. Part 8. Loop Quantum Cosmology and the Big Bounce. As we continue our tranquil journey through alternative cosmologies, let's explore loop quantum cosmology (LQC) and its implication. The Big Bounce, a theory suggesting that the universe's origin stems from a previous contracting phase, leading to a cyclical pattern of cosmic rebirths. Understanding loop quantum cosmology. Loop quantum cosmology is a finite symmetry-reduced model derived from loop quantum gravity (LQG), which attempts to quantize spacetime itself. LQC applies these principles to cosmological settings, aiming to understand the universe's behavior at the smallest scales. A key prediction of LQC is the replacement of the classical Big Bang singularity with a quantum bounce, suggesting that the universe undergoes cycles of contraction and expansion. So key features of loop quantum cosmology. Quantum geometry. LQC introduces a discrete structure of spacetime at the Planck scale, leading to a repulsive force that prevents singularities and causes a bounce instead. So a big bounce. The universe's contraction reaches a minimum volume, after which it transitions smoothly into an expansion phase, avoiding the infinite densities predicted by classical general relativity. So a predictive power. LQC provides testable predictions, such as specific imprints on the cosmic microwave background radiation (CMB), which could potentially validate the theory. So challenges to loop quantum cosmology. While LQC offers an elegant resolution to the Big Bang singularity problem, it faces challenges. So empirical validation. Detecting the predicted imprints on the CMB requires highly sensitive measurements, and current observations have yet to confirm these signatures conclusively. So theoretical development. As a relatively new framework, LQC continues to evolve, and its integration with the broader context of quantum gravity theories remains an ongoing endeavor. So pariter. As you contemplate this model, imagine the universe as a phoenix, eternally rising from its own ashes, with each cycle of contraction and expansion giving birth to new cosmic epochs. Part 9. The Cyclic Model and the Big Crunch. As we continue our tranquil journey through alternative cosmologies, let's explore the cyclic model, a concept proposing that the universe undergoes infinite cycles of expansion and contraction, each culminating in a big crunch, followed by a new Big Bang. Understanding the cyclic model suggests that the universe experiences endless cycles, each beginning with a Big Bang, expanding over billions of years, and eventually contracting into a big crunch. This contraction leads to conditions similar to those at the universe's inception, triggering a subsequent Big Bang and the birth of a new cycle. This model offers an eternal, self-sustaining cosmos without a definitive beginning or end. So show key features of the cyclic model: eternal cycles. The universe perpetually oscillates between expansion and contraction phases, with each cycle giving rise to the next. So resolution of singularities. The model proposes mechanisms to avoid singularities, such as the Big Crunch leading smoothly into a new Big Bang. Social alternative to inflation. The cyclic model provides a different explanation for the observed homogeneity and flatness of the universe, challenging the necessity of cosmic inflation. Social challenges to the cyclic model. While the cyclic model offers an intriguing perspective, it faces challenges. Social challenge: accumulation. Each cycle must address the accumulation of entropy to avoid a heat death, where the universe reaches thermodynamic equilibrium and cannot sustain further cycles. Social challenge: piece of observational evidence. Current observations, such as the cosmic microwave background radiation, align more closely with the predictions of the Big Bang model, posing challenges for the cyclic model. Social challenge: repeat. This model, imagine the universe as a cosmic heartbeat, rhythmically expanding and contracting, each pulse giving rise to new realms of existence. Part 10. Eternal inflation and the multiverse. As we conclude our tranquil journey through alternative cosmologies, let's explore the concept of eternal inflation, a theory suggesting that cosmic inflation, the rapid expansion of the universe after the Big Bang, continues indefinitely in various regions, leading to the creation of a vast multiverse. Understanding eternal inflation extends the standard inflationary model by proposing that inflation does not end uniformly across all regions of space. Instead, while inflation ceases in some areas, allowing for the formation of galaxies and stars, it persists in others. This ongoing process results in the continuous creation of pocket universes, each potentially possessing distinct physical properties and constants. Key features of eternal inflation: self-reproduction. Quantum fluctuations during inflation can lead to regions where inflation continues indefinitely, causing the universe to self-replicate and produce an infinite number of pocket universes. Diverse universes. Each pocket universe may have different laws of physics, depending on the specific conditions present when inflation ended in that region. Vast fractal structure. The multiverse resulting from eternal inflation exhibits a fractal-like structure, with inflating regions continually spawning new universes. Implications of eternal inflation. The theory of eternal inflation carries profound implications. The anthropic principle. vast number of universes with varying properties could explain why our universe appears fine-tuned for life. We exist in one of the rare universes where conditions permit our existence, 2D and servable realms. Most pocket universes would be beyond our observational reach, challenging the notion of a single, observable cosmos. 2D and philosophical considerations. The existence of a multiverse raises questions about the uniqueness of our universe and the nature of reality itself. 2D and philosophic on this concept. Imagine the cosmos as an ever-expanding sea of bubbles, each bubble representing a unique universe with its own distinct characteristics, floating in the boundless expanse of the multiverse.